Compare data formats: XML, JSON, and YAML. These are the primary ways applications structure and exchange information. Think of them like three different writing systems: one formal like Latin, one simple like English, and one lightweight like shorthand. At their core, they let systems communicate clearly, just like people using agreed-upon grammar and style rules. XML is like a legal contract, verbose, strict, and well-suited for highly structured documentation. JSON is like a quick text message, simple, clear, and widely used in modern APIs. YAML is like a recipe card, human-friendly, easy to read, but still precise for automation. Choosing the right format ensures efficiency, readability, and compatibility between systems. From configuration files to API payloads, these formats define how software components talk. Mastering their differences ensures smooth integration in any modern software project. Parsing data formats into Python means turning text like XML, JSON, or YAML into usable Python objects. It's like translating a foreign language book into your native tongue so you can actually understand and use it. In development, we need this translation because data often arrives as text, but our code works with lists, dicts, and objects. XML parsing produces nested structures, like dictionaries inside dictionaries, representing tags and attributes. JSON parsing maps directly into Python's dictionaries and lists, a perfect one-to-one translation. YAML parsing gives clean, readable structures, like configuration dictionaries, without extra symbols or complexity. This transformation lets developers process, search, and modify information efficiently. Whether handling an API response, a config file, or automation script, parsing bridges the gap between raw data and actionable logic. It's the key to connecting external data with Python-driven solutions. Test-driven development, or TDD, is a method where tests are written before the actual code. Think of it like designing a car's crash test before building the vehicle. Safety defines construction. This approach ensures that software is guided by requirements, not assumptions, leading to cleaner, more reliable results. The first step is writing a failing test, a statement of what the software should achieve. Next, developers write just enough code to make the test pass, no more and no less. Then, they refactor, improving structure without breaking functionality, ensuring maintainability and readability. This cycle of red, green, and refactor keeps development focused and predictable. TDD benefits include fewer bugs, higher confidence in changes, and easier collaboration. Across projects, it ensures software behaves exactly as intended, reinforcing trust between developers, testers, and users. Software development methods define how teams plan, build, and deliver projects. Agile, lean, and waterfall are the most common. Think of them like planning a trip: strict itinerary, flexible backpacking, or minimal essentials. Each style shapes the workflow, speed, and collaboration of the team. Waterfall is sequential, like building a house where foundation, walls, and roof must follow in order. Agile is iterative, like cooking and tasting at the same time, adjusting ingredients as you go. Lean focuses on eliminating waste, like packing only what you truly need for a journey. These methods matter because they affect cost, quality, and speed of delivery. Enterprises may choose waterfall for strict projects, agile for adaptable products, or lean for efficiency. Understanding these models helps developers align with organizational goals and customer needs, ensuring projects succeed with the right balance. Organizing code into methods, functions, classes, and modules creates cleaner, more manageable software. Think of it like arranging a library. Books grouped by subject are easier to find than a random pile. This structure makes code predictable, reusable, and easier to test or debug. Functions are like recipes, reusable sets of steps for specific tasks. Classes are like blueprints, defining objects with both properties and behaviors. Modules are like labeled boxes, packaging related tools together for better organization. This modular design makes teams more efficient, reducing duplication and simplifying maintenance. From small scripts to enterprise applications, structured code improves collaboration, readability, and scalability. It's the foundation of professional development. Without it, projects quickly become unmanageable. Design patterns are proven solutions to recurring software challenges, saving time and ensuring reliable results. It's like using architectural blueprints. Why reinvent the wheel when proven designs already exist? They make software easier to understand, extend, and maintain across projects. The MVC pattern separates code into model, view, and controller, like dividing a restaurant into kitchen, menu, and waitstaff. The observer pattern links objects so changes automatically notify dependents, like news alerts sent to subscribers. These patterns encourage loose coupling and better collaboration between components. They're widely adopted in frameworks, making learning and contributing faster. From web apps to distributed systems, design patterns keep code robust and adaptable. Recognizing and applying them ensures solutions are both efficient and scalable. Version control systems record and manage changes to code, enabling collaboration and safety. It's like a time machine for your project. Every step is saved, nothing is lost. This matters because code evolves constantly, and teams must stay aligned without overriding each other's work. Version control lets multiple developers contribute simultaneously, resolving conflicts when changes overlap. It preserves history. You can revisit, compare, or restore any previous state of the project. It also supports branching, experimenting safely without harming the main code. This makes development faster, safer, and more flexible. Whether in solo work or large-scale collaboration, version control ensures stability and confidence. It transforms chaotic edits into a structured, auditable process, critical for modern software engineering. Git clone. This operation creates a local copy of a remote repository for development. It's like photocopying a book. You get a full copy to work with independently. This step matters because most projects are hosted remotely, and we need them locally to contribute. Here our objective is simple: retrieve the full repository to our system. We'll use Git, the standard tool for distributed version control, to clone a project. Running the command copies all files, history, and branches into a new local folder. The output confirms objects and commits were received, ensuring a complete copy. Now developers can explore, edit, and experiment offline while keeping the original remote untouched. Cloning is always the first step when joining a new project, providing the foundation for collaboration. Git add and remove. These commands manage which changes are staged for the next commit. It's like packing a suitcase. You decide what to take along and what to leave behind. This process matters because only staged files are recorded in the next snapshot of the repository. Our objective here is to prepare new files and remove outdated ones from version control. Using Git, we stage additions with add and delete obsolete files with rm. The actions don't yet alter history, but prepare changes for the upcoming commit. The output confirms files staged or removed, giving visibility into the project state. This ensures only relevant updates move forward while clutter is eliminated. Mastering add and remove keeps repositories organized, reflecting exactly what the team wants to preserve. Git commit. This command saves staged changes into the repository's history with a descriptive message. It's like writing an entry in a diary, capturing what happened at a specific moment. This step matters because without committing, changes exist only temporarily and can be lost or forgotten. Here the objective is to create a permanent snapshot of modifications in the project timeline. Using Git, we run commit with a message describing the purpose of changes. The system records updates, assigns a unique ID, and logs details into history. The output confirms what files changed and how many lines were added or removed. Commit messages provide context, ensuring clarity for collaborators and for your future self. Frequent, meaningful commits keep code transparent, traceable, and easy to manage across development cycles. Git push and pull. These commands synchronize local work with the remote repository. It's like uploading photos to the cloud and later downloading the newest versions to your phone. This process ensures everyone's code stays updated and conflicts are minimized. Our objective here is to share local commits with the remote and fetch others' contributions. Using Git, push sends changes outward while pull retrieves updates into the local copy. The tool shows whether commits were transferred successfully or if updates merged automatically. The output lists changes, commit IDs, and whether the repository advanced. Push and pull maintain alignment across distributed teams, preventing outdated or isolated code. Together, they form the backbone of collaboration, keeping projects consistent and up-to-date. Git branch. This feature creates isolated environments within the same repository for focused development. It's like drafting chapters in separate notebooks before assembling them into the final book. Branching matters because it allows experimentation without disrupting the main project's stability. Our objective here is to create a branch dedicated to developing a new feature. Using Git, we make a branch and switch into it for independent work. The repository now tracks changes separately, preserving the main branch untouched. The output confirms the active branch name and successful switch. Branches empower teams to work in parallel, test ideas, and merge when ready. This flexibility is a cornerstone of modern version control, boosting productivity and safety. Git merge brings work from one branch into another, creating a unified project history. It's like combining two drafts of a story. Sometimes the edits overlap. This matters because collaborative work often requires integration of multiple features at once. Here the objective is to merge a feature branch back into the main branch. Using Git, we issue the merge command, letting the system combine changes automatically. If two people edited the same section, conflicts occur, requiring manual resolution. The output shows which files need attention and whether the merge succeeded. Handling conflicts ensures no code is lost and that everyone's contributions are preserved. Mastering merge is essential for smooth teamwork in shared repositories. Git diff displays differences between versions of files, showing what changed. It's like using track changes in a document, highlighting additions and deletions. This matters because developers must review edits before committing or merging them. Our objective here is to inspect changes since the last commit. Using Git, the diff command shows modifications line by line. The output highlights removed content with a minus and new content with a plus. This makes it easy to understand exactly what was altered. Diff helps developers verify accuracy, catch mistakes, and review contributions. It's a powerful tool for quality control and collaboration.